Next we have a presentation by André from Segment Synth.
Hello everyone, thank you for coming. I shall be presenting the project which we have been working on for the past year, almost full time. It's called the Segment Synthesizer. It's an open source and open hardware digital synthesizer. It's still a prototype, but it's almost there. As you can see, it's all messy on the table. This is us. This is me. This is Michael. He's sitting somewhere there. And this is the other two members of our team who unfortunately couldn't come because they had other things. So just briefly say what each of us are doing. I'm responsible for the DSP part of the synth and the synthesis itself. Michael is doing the hardware bits, putting things together, designing them so they all communicate and work well. Amir is mainly responsible for the USB host, which we had to implement ourselves. I certainly couldn't do it, and I don't think Michael could. And Martin is responsible for all the software bits. That is including the segment synth, the segment cloud, and the segment manager for storing presets and loading them and managing all this. First, let's talk a bit about what's important about this synth, what's new, what we think is the killer feature, well, one of them at least. The synthesis method. We call it the segment synthesis. And it works the way that we thought that the goal was to create as thick and harmonically rich sounds as possible. So to do that, we thought how we do things now with our EDM productions and dubstep music and whatnot. And we realized that you just end up stacking up on top of lots of saw waves and square waves and then doing choruses and flangers and distorting everything, distorting every channel. So we wanted to tackle this problem right at the beginning, at the synthesis step. So we decided that, we thought that in order to get the information out of a single waveform, only half of it is needed because, that's regarding the square wave and the sine waves, because the other part is just repeating itself in an inverted way. So what we do is, let's take a simple example. We take these 4 waveforms and we slice them up vertically. Now, all these waveforms are tuned to the same frequency. They're all the same size, all the same amplitude, just for the sake of the example. You slice them up and you render them on an ongoing oscillator like this. This is the simplest case of the segment synthesis. We are also doing frequency modulation to the individual bits, to the individual segments, and panning to the individual segments. So you end up with a lot of more harmonic content than you otherwise would with the usual additive or subtractive synthesis. This is an example. The picture on the top is the additive synthesis using the same waveforms I've showed you earlier, and they're just stacked on top of each other. And this is the segment. As you can see, there's far more harmonic content. Of course, the fundamentals stay, but there's lots of more stuff going on there. And this is because by segmenting, you create these edges, these rough edges, which are the carriers of harmonic content. Because, the sine wave is just a sine wave. There's just one fundamental. But as soon as you break it and create the rough edges, you get harmonics. This brings problems, of course, such as aliasing, which we try to tackle in many ways, but in the end decided not to tackle it at all, because it sounds so thick and dirty anyway, so we decided, okay, it just stays. And when we were testing it and playing around with it, we thought that you can create actually some cool effects with it, so we sort of stopped caring about that. Now I said that for each of the segments, you can adjust the panning, the frequency modulation, and also the waveform. You can blend one of 4 waveforms, that's saw, square wave, sine, and the reverse saw, and you can blend them not stepwise, but you can really blend them. Also for each of the segments you can adjust the panning, as I said, and also the amplitude. Now the frequency modulations, when I first designed the segment synthesis, I didn't very much know how frequency modulation works. So I ended up doing it in a way, and then I discovered that I was doing it the wrong way, but then it stayed because it sounds completely different. So this is the usual on top of what you have. Phase modulation, you could go, if you will. A basic example with a sine wave, and you end up with a very nice and periodic content in the waveform. Of course, with the added harmonics. This is what we do. We instead of adding, we multiply. So as you can see, it's not periodic at all. If you just run it on the oscillator forever, it's just noise, a very ugly one. But if you reset it every 2 pi, you get periodic because it always ends on 0 on 2 pi. For reasons which are unknown to me. Well, it is like it just does, yeah. So let's have a quick view on the segments and how, so you can, because what I described you earlier, it's how we slice them up. It's one of the implementations. You can slice them up in halves. You can do whatever you like. So the way we implement it is a bit different, but the implementation differs. So. A sec. Okay, so I'll mute it so we just can see. Can you see the waveforms actually? Yes. Okay, because I don't. So let's just. I'll pretend I can see them too. So. So now I bring down all the segments. And the reason why it's synced is because we have found the exact frequency at which the oscillator is in sync with the refresh rate of the oscilloscope, the waveform render. So this is I shall be bringing up. We shall be not applying any frequency modulation as per now, and I'll bring up the first segment. It's not really a segment; it's the whole thing. Okay. So this is it. Good. And there's also some sub-octaves which I shall bring down. Okay. So this is the whole period. You can blend the waveforms, square wave, sine, and reverse. Right. So I'll leave the saw on so we know where it begins and where it ends. I mean the period. So now I shall bring on the first segment, which is this one. It is the first half. Maybe it'd be better if I do it like this. Like so, for example. So the first segment is first half of the period. Then we have a duplicated segment, which gives you the opportunity to pan it left and right. The next 2 segments are at 3/4. I shall bring one of them up. This is it. Okay. Again, blend in the waves any way you like. There's two of them for panning. And the last bit is, well, what's left of it. Like this. Again, sorry. Okay, so let's look at the, because it is understandable, I think it's pretty straightforward. Let's look at the frequency modulation. I should bring all of them down. And we'll look at frequency modulation only at the whole segment, so we can hear what it sounds like. Let's look at a different segment with its frequency modulation, and then I will show you some examples, live sounds examples, of what sounds you can do with it. Okay, so now we're playing only half the period. This is how the frequency, what it does to the signal. If you push it too high, it will go into aliasing. Well, you'd have to play a higher note, but it's true. Okay, let's do some sound examples. We have a small problem here. Can you hear it? Is it loud enough? One of the things that it's one of the features that it does by design is, since the harmonic content is so high, if you downtune the synthesizer a lot, so the fundamental frequency is way below what you can hear, there's still enough harmonic content, you can hear it going. So let me demonstrate that. like that. So. Let's have some information about the controls. Unfortunately, you cannot see that from your point of view, but I can, and the camera will, so it's fine. This is all the controls the segment has button-wise, and let's walk through them. All of them are silicone, custom-molded silicone pads, which I can. It's similar pads that you can find on most of the controllers. I shall pass them on. We have plenty, but please don't break them. They're pretty durable. So the second killer feature, well, what we believe is the killer feature, is the LFO that is always synced to the master BPM. These buttons control it, and you select which division of the BPM you're using. The 0 is obviously off, and then full note, half note, quarter note, eighth note, triplet, and so forth. Even if you select 0, which means you're bypassing it, the LFO still goes on, but it's not affecting your signal. So for all these the rhythmic stuff, you will always be in sync. For example, if you're in sync with your MIDI time clock, or if you have tapped your rhythm, or via control voltage ticks, whatever you like. With the second part of the LFO controls, you select the waveform of your LFO. Again, the important thing is that it always stays in sync. For each of the presets, there's 12 presets in total, and for each of them, you can have 5 sounds. These sounds modify the parameters of your synthesis. They don't modify your filters, nor your portamento glide settings, nor your drift, which we'll be talking about later. They select your sound. So if you can see the way the controls are designed, and it all fits within one hand, even if it's a small hand. For each note that you play, you can select a different LFO speed, a different LFO waveform, and a different sound. So you can do these triple taps and create pretty wild stuff with it. Let's take a small side path and talk about the encoder and the displays, so you can see what settings we apply. We have 8 OLED displays, and above each of them is an encoder. Originally we had LED rings around each of the encoders, but because this is way cooler, and also because the LEDs are expensive, we decided to go this way since we already have the displays. So for each value you have this bar graph that says what value you're at. Now with that we see what values and how you see them, let's look at the controls that modify these values. First, these 3 buttons select the layers on the display, and they allow you to modify the parameters of the synthesis for different segments. So for example, the first button is for each of the segments, it's waveform, pan, amp, and frequency modulation. So for the first button, you modify the first segment, which is the whole, and the last bit, like I showed you before. For the second button, first 2 halves, and for the third button, first 2 3/4, as per the button image. These are others. So you can see there's a play stop button. It's just play. What it does is it actually stops the LFO. So when I said the LFO keeps running forever, so the light, this can stop it. And this is useful, for example, if your drummer starts playing, you tap to his rhythm, and you run the LFO on the first bar, so you stay in sync and also in time, in phase. The button with the exclamation mark is, we call it a user button, and you can map it to any of the buttons on the encoders, because each of the encoder, you can also press it, and so for some parameters, if you press it, it resets to 0, and for some parameters, it resets to the value that you have set in your preset. So if you mess about and you mess it up, you can always return to where you started. Envelopes, settings, and linker and scaling for the linker. I shall be talking about that later on. Now the presets. If you press this icon, which we hate, but decided to use that anyway because it's widely used, you can select your presets, and then all these buttons become your preset buttons. So if you want to load a preset, you click the diskette icon and select one of your presets. It's very quick, so you can immediately access lots of sounds, including these 5, because for every preset there's 5 different sounds. Good. So let's talk about the drift. What we initially thought the synthesizer plays, even though the sounds are wild and thick, they're sort of static. And what we love about analog synthesis is its instability. And we wanted to implement that somehow in our synthesis as well. So we did this drift feature. And this is, again, just for the sake of demonstration. Let's say you have a volume parameter and the drift parameter. In reality, the drift parameter modifies the synthesis parameters, but let's just, for now, say that it will modify the volume parameter. So if you set your drift to a low value, it will drift the volume value around its set point to the size of which you have set the drift on. The higher you set the drift, the bigger the instability will be. And because we don't want to have so many parameters for everything, the drift parameter by itself modifies the amount of drift, also the polling speed, which means how often does it select its new target for the parameter, and the drift speed, how fast it goes to its newly selected point. Is that clear? Is that good? So for the hardware bit, let's talk about hardware a little. We're using our ARM Cortex M4 for audio, the chip, and it's bare metal. There's no OS, so sorry to disappoint all the Linux souls in us. We decided not to use any operating system because we're already the chip is running in 168 megahertz, so it was already pretty tough to optimize it so heavily so it runs. Then it uses, again, Cortex for encoders and displays, and M0 for buttons and RGB LEDs. M0 obviously because there's no need for a CPU that is so powerful. And the digital analog converter is 24 bits 48, and this is the same sampling rate with which the synthesis and the whole synthesizer runs. Software. As I said, we're running bare metal. For the library, peripheral library, we're using libopencm3. We at first tried to use the ST Electronics supplied, but it didn't have an appropriate license for us. And since we want to distribute this with GPL and the whole thing, and we have forked the libopencm3 to include the USB host module, we decided to use that instead. And the community is lovely. 32-bit flow processing, and what's interesting is that it also, of course, it accepts MIDI, and we also implementing open sound control. But the MIDI it receives from the internal controls are 10-bit. It just looks the same as the MIDI message. It has the same status bytes and data bytes, but it's 10-bit. So we have a bigger range. It was the 7-bit MIDI is more than enough for most of the things, but for the FM you could hear the steps because it adds the harmonics this way. Another interesting thing is that we use zero buffer. So when the the MIDI message gets to the synthesizer, it reacts immediately. There's no buffering, no latencies, apart from what you add on top of it, of course. This is what it will look like in the future when it's finished. You can see two USB hosts to connect your USB keyboard, such as this, or other USB controllers. It has a USB device, so you can connect it to your computer, such as I am now, also. Balanced output headphones, 4 control voltage input, and 2 control voltage output. You can, of course, interconnect them, and you can route these control voltage signals to any of the parameters. Another thing is that each parameter has its own MIDI CC, so you can control the whole synthesizer. You can just put this somewhere in a box, don't look at it at all, and control it all externally. Also, for this reason, the size of the synthesizer is 2 rack units high and half rack wide, so you can put it in your rack, embed it inside, or maybe put 2 segments next to each other. The control voltage, of course, allows you to not just interconnect it to itself, but also connect it to other modular devices. And we shall be using an external power supply because the height of the synthesizer you can see now is the same as it will be. So we didn't want to compromise the height to include a power supply. One of the software features that I'd like to talk about a little is the segment cloud. It is similar to the mod cloud. Hello. And it will allow the users to share their presets, their sounds. One of the differences is that we will be rendering the audio offline. Because it doesn't act as an audio interface, as a USB audio interface. So you will connect it, it will read your MIDI, send it to the server, which runs, it's basically the same code with just a few mods, because some of the bits are not portable. And it will render an OGG or WAV file or whatever on the server in the cloud. This is what the current version looks like, but you might expect it would look something like this. You register your user, upload stuff, look at the waveforms, comment, like, share, and whatnot. Yes. Licensing. As I said before, we'll be using GPL3 and the open hardware license, the APR, which we have found out just only recently. For those who don't know it, it's just like GPL, it's viral, except it's for hardware. It needed to be written, thank you very much. It needed to be written separately because some of the bits I'm not right. We will be crowdfunding this on Indiegogo, and when we do that, we'll release all the sources and all the hardware documentation, including the schematics, the CAD designs for the pads and for the front panel, and all those things. And we expect the campaign to start in May 2015, which is some short time from now. I shall demonstrate so we can hear more of the stuff. I would like to show you the drift feature. So, okay. It's just a note. So now the drift is 0. I shall be adding it slowly. So you can either go gently or just break up the sound so it doesn't look like anything like the sound you heard before. Yes, question, I see the question, yes. The pitch? No. Would you like that? No, you cannot. The drift, it destabilizes the synthesis parameters. It's always on the note you are playing. And we designed it that way, we like it that way. So when you just always stay in tune. Yes?
What kind of noise are you using for the drift?
We use a randomly generated table of numbers, and we just select on those. There's about thousands of them, and it seems enough.
Do you prefer a specific spectrum for these noise? Is it rather slowly random, or are they high frequency random?
That depends on how much you turn the drift up.
You change the spectrum
yes.
of the random numbers when you tune up the drift.
Well, not this. Oh, you mean the distribution of
Yes,
the random?
yes.
No, it's just random.
That's fixed.
STD random from C++.
Ah, okay.
Yes. Sorry, I thought. Yeah. So this is the drift. We also have something we called the side cut filter, because we here it's. I'll back this up. It's one knob, and you can filter it. This is the different filter, not the LFO filter, which I'll show you in a minute. The side cut filter, it's a low pass or high pass on one note, one knob. So if you turn it leftwise, you cut your highs, and if you turn it the other way, if you press it, it resets. So you can do these pre-chorus, pre-drop sweeps, and then reset it on the beat, because we like that. We'll show you a bit of the LFOing now, because that's one of the things we love, and it's once you get used to it, it's very easy to play, it's intuitive, and it's fun. Let's do more sounds with the A, B, C, D buttons, and we shall be switching between those also. So this is the A sound that I already made. Let's leave it at that. Let's configure the B sound, which I'll just make. Okay, that was the B sound. Let's have the C sound. It's still on the same note, so it might. Also, if you use the glide parameter, I will show you how you can sync it with your MIDI time clock. Like, I have here a drum loop from Hydrogen. It's lovely. You'll love it. The sync is on. Now it's on. Okay. Good? It's really good. So let's hear the... Okay, that's not. I have reset it. Every time you reset it, you just... Now I'm driving the synthesizer with a sequencer from the computer and listening to the drum beat from the computer and syncing with MIDI time clock. So you just select it to sync and it listens to the messages. Since we are running out of time, it seems, I'd like to show you. This is where you can find us: Twitter, Facebook, and our webpage, segmentsynth.com. I would like to thank Michael because we have been working for the past 2 days to finish some of this stuff so it's presentable like it is hacking on it. Do you have some questions regarding anything really? Yes?
Yeah, amazing. The presets, are they saved on the device? So is there storage on the device itself?
Yes, there's EEPROM on the synthesizer that stores all of that.
So is it monophonic only, or is it polyphonic?
It's monophonic. One of the reasons is because we really want to target it at the EDM bass sounds or the EDM fat leads. So you don't do that anyway, and the sound is so thick. If you did a triad or even a fourth, it sounds just ugly.
Is the drift parameter displays the border of the segment?
No. I'm sorry, it's not part of the synthesis itself, but it's there. Was that the question? Yes? It's not part of the segment synthesis in itself. It's just sort of a meta-external module that modifies the parameters of the synthesis. Okay?
Any more questions? IRC, yeah?
Yes, up there. Yes, price. We expect this to be around 320 euros for the Indiegogo campaign. And when we go, hopefully, full production, it will be higher than that. Does that satisfy you? Okay, great.
Okay, last question from IRC.
How much is the final hardware going to cost?
That was the question that you're late. 320, around that. Yes?
Well,
have you got an idea of how you're going to automate or how are you going to do the production? Where do you want to do the production?
All those parts that we have, well, vast majority of them are already made in such a way that we all just say to the manufacturers of these, we say, yes, this is great, make lots of that. Does that satisfy your curiosity? It's most of that is in the far east.
I'm sorry to say we don't have more time for questions, so thank you, André.
Thank you very much, and also my grandmother.